What's up, amigos? Today we have a very interesting simulation here. It's probably one of the most surprising, if not the most we've done to date. It's of a rock, but it's not what you'd think. So to begin with, we first did the simulation to see how well a rock flies. So what velocity do we need to throw it at to produce enough lift to overcome its weight? But as we started doing the simulation, it became obvious that this rock is not like other rocks, or at least not like other objects. If you've seen our other CFD simulations, you'll see quite a big difference here. So I'll let you guess what it is before I go into the actual details. As for the lift and drag and all that, so as I mentioned, we wanted to see how well it produced lift, and we found that the downforce on this was minus 0.027, the lift coefficient, so it's negative there. So that means that if you wanted to make this thing fly, you have to turn upside down and throw it at a velocity of 82.3 meters per second. So it is doable. You can make almost anything fly as long as you throw it fast enough. The drag coefficient is actually really low. It's 0.3922 for a rock. And this gives us an idea as to what's going on here. So the drag coefficient of 0.39 is significantly lower than what I'd expect. I'd expect maybe like 0.6, 0.8 kind of thing. But these cut planes downstream of the rock indicate why we're getting such a low drag coefficient. So have you noticed something weird about these wakes, these slices? The thing that I've noticed is that this is a bluff body effectively, and the wake is quite bluff body-like in terms of it is very big, but you'll notice that there is very little unsteadiness. It's quite steady, like there's a little bit of meandering about of these different wake cores, but generally speaking, it's much better than most other bluff bodies. And why is that? The reason why is because the rock is very rough on top. So you can see that there are all these little jagged points coming off. So this means that it's turbulating the flow enough so that the separation point on the rock is fairly steady. Let's look at some other planes to see how this occurs. So now we have a Y plane going through the middle of this rock. And we can see again just how small the wake is downstream. So directly behind the rock, it's fairly big, but it sucks in very nicely, and it doesn't wiggle around too much, which indicates that there's not much of von Karman happening. And if you look close to the surface, the point at which the flow separates over the surface is approximately about halfway on top, and it doesn't really fluctuate too much around. If you were to contrast this to, let's say, a cylinder, which we've done a bunch of von Karman simulations on that, so you can see in the link here, you'll see that with those ones, the point at which the flow separates oscillates around quite a lot. On this one, it doesn't, and that's because of these jagged points. These jagged points act as a definite location where the flow will separate. It doesn't move back and forward, upstream and downstream, as you would have for other smooth surface bluff bodies. So now we have a Z-plane about halfway up, and it shows a very similar thing where the wake is fairly big to begin with, but it sucks in quite well, and it is quite a red downstream, and it's very steady. So there's only a little bit of meandering about, and you can see the flow over the rock stays, like the separation points stay fairly constant at about halfway downstream of the leading edge, or the front of it. And these jagged parts, again, they control the flow very well. So if you make the roughness like pretty much macroscopic, you can effectively control where the flow separates. So that's the end of the simulation. And just to recap, the velocity that you need to throw this rock at to make it fly is you have to turn it upside down and throw it at 82 meters per second. And the drag coefficient is under 0.4, which is about as good as some cars. So make sure to like, subscribe this, and if you want to get better at CFD yourself and or theory, check out our courses in the link in the description. And I'll see you in the next simulation. Peace out, amigos.